Welcome back to the second video in our final exam review. Today we're going to be talking about two more examples where we're working with L'Hopital's rule. So in the last video we talked about what L'Hopital's rule is, and we saw a few simple examples where we have a limit of f of x over g of x that is in an indeterminate form. Now what we're going to see in this video are limits that are not of this form, f of x over g of x. All right, so let's go ahead and take a look at our first example. We're going to take the limit as x approaches 0 from the right-hand side of x times the natural log of x. The first thing that we may want to note is that we're taking the limit as x approaches only from the right-hand side, and the reason for this is that the natural log is not defined whenever x is 0, so it doesn't make sense for me to approach from the left-hand side. All right, the second thing that we might notice is that this isn't in the form that we've seen in the previous video. Instead, what we have here is x times the natural log of x. It's not f of x over g of x. So what we're going to do is try to rewrite this into the form of f of x over g of x. And the way that we're going to do this is by taking this simple fact that we can write x as 1 over x. All right, and we can see already that this is going to allow us to take our limit and rewrite it into the form f of x over g of x. But before we do that, let's go ahead and just take a look at the limit. All right, as I send x to 0 from the right-hand side, of course this term x is going to approach 0. Secondly, as I send x to 0, the natural log of x gets smaller and smaller and smaller. So as x goes to 0, natural log of x is going to go to negative infinity. So this looks something like 0 times negative infinity in determinate form. Okay, so this isn't an indeterminate form that we've seen yet. All right, so then let's go ahead and try to simplify this limit into a form that we have seen. So the limit as x goes to 0 from the right-hand side of x times natural log of x. And I'm going to use the fact that I can write x as 1 over x to rewrite this as the limit as x goes to 0 from the right-hand side of natural log of x over 1 over x. Okay, now this looks like a function f over another function g. So let's see what happens. Let's kind of look at the behavior of the numerator and the denominator. As I send x to 0, natural log of x is going to go to minus infinity. All right, furthermore, as I send x to 0, the denominator now is going to also go to infinity. All right, so this gives me an infinity over infinity indeterminate form. All right, perfect. So now that I've rewritten this in infinity over infinity type indeterminate form, that means that I can just go ahead and apply L'Hopital's rule. So I need to differentiate the numerator, and I need to differentiate the denominator. All right, so derivative of ln of x is 1 over x, and the derivative of 1 over x is minus 1 over x squared. All right, and then finally simplifying this gives me minus the limit of x going to 0 from the right-hand side of x. And of course, this just evaluates to the 0. All right, and the last example we're going to look at is the limit as x goes to 0, again from the right-hand side, of arctan 2x over the natural log of x. All right, now this isn't a form of a function f over another function g. But again, we want to make sure that the assumptions of L'Hopital's rule are true before we actually go ahead and apply L'Hopital's rule. Right, so let's make sure that this is actually true. So what am I trying to show? I'm trying to show that I have an indeterminate form 0 over 0 or infinity over infinity. All right, so as I send x to 0, what happens to the function arctan? Well, to help us kind of figure out how this function behaves, I drew the graph of this over on the right-hand side. So I can see as I approach 0 from the right-hand side, the blue line, the graph of arctan, looks like it's approaching 0. And that is in fact the case. As I send x to 0, arctangent goes to 0. All right, now what happens to the function natural log as I send x to 0 from the right-hand side? Well, from the previous example, we know that this is going to go to negative infinity. So what do we have? We have 0 over negative infinity. Right, so now you might be convinced that we need to use L'Hopital's rule, but remember the indeterminate forms that we know how to work with are 0 over 0 and infinity over infinity, and that is not one of the cases that we have here. Right, so how can we solve this limit then if we can't apply L'Hopital's rule? Right, so let's go back and use an idea that we did in the first video. So what we're going to do is just take this limit as x approaches 0 from the right-hand side, 2x over natural log of x, and let's break it up into the product of two limits and see what happens. All right, so we did this in one of the example problems in the first video because it made it a little bit easier for us to apply L'Hopital's rule to whatever was left over. All right, so this is going to give us the limit as x goes to 0 from the right-hand side of arctangent of 2x times 1 over natural log of x. All right, we can take this one step further and break it up into two separate limits. Limit as x approaches 0 from the right-hand side, arctangent of 2x times the limit as x approaches 0 from the right-hand side, 1 over natural log of x. All right, so let's go ahead and take a look at this first limit. So as I send x to 0, what happens to arctan? Well, arctan is a continuous function at 0, and so I can just use the substitution rule. This is going to be equal to 0. All right, now what happens as I send 1 over ln of x as I send x to 0? Well, I notice that the denominator is going to go towards negative infinity. So as the denominator goes towards negative infinity, this entire quantity is going to go towards 0. So what am I left with? I'm left with this limit also being equal to 0. All right, so now if I multiply those two together, I have that this is equal to 0. All right, so we can see that we actually didn't need to apply L'Hopital's rule here, and it wasn't actually possible for us to do that because we didn't have an indeterminate form. Instead, we can just use some of the basic properties that we learned about limits earlier on in this course to simplify things to a state that we could actually solve it. All right, so in the next video, we're going to talk about how to approach optimization problems, and we're going to see a few examples of how we can actually solve some of those problems.